Okay, first up, remember that you can go up onto Canvas if you've missed or you're late or whatever and go through the notes again if you've missed them. I'm trying to put one up for each period, but sometimes I only get one up per period or one up for all 3 periods, so make sure you check that. You should have been turning in your separation analysis. That is actually due by 11:59 tonight, so make sure you get it up and in. I've only got like 6 in. The lab. Okay, so lab is due by 11:59 tonight, so make sure you get it in. Okay, today we're going to go on in Chapter 5, Balancing Equations, Types of Reactions, Solubility Rules, and focus on health and medicine and pacemakers. Now you'll notice your Learn Smarts, you should have done the first 2. Should have done the first 2. Now the next 2 are due, so if you're falling behind, get them caught up over the weekend. The Learn Smarts are fairly easy, shouldn't be too rough on you, so make sure we get those done. All right, so types of reactions. Come on up. We'll sign you in real fast. Okay, go. Okay, types of reactions. We do have 2 types of reactions that we're going to go over. Main groups are, as I fall over the garbage can, it's been that kind of morning too. Non-redox and non-redox and redox. There's only one really true non-redox, and that's a double displacement. I'm not going to spend a lot of time on these types of reactions because we're going to go over them again on Monday. So I'm going to go through this part fairly quick, so stay up with me. Whoops. On the other side, we've got redox. And you see redox and non-redox sort of overlap for 2 of them. Single replacement and, whoa, this really loves me today. Okay, combination or combustion, single replacement and combustion are the only true redox. And then we've got decomposition and combination, also known as synthesis. Those are the ones that can go either way, depending on if we go down to an element or if we are starting with elements, then they usually are redox. If we don't start with an element or don't go down to an element, then they're usually not redox. So this is the overall arching of all the different types. And then we're going to go in and talk about each type just really quickly, because next time I'm actually going to do some demos with each kind, and you can sort of see what each kind looks like. Okay? So that's what next week is. We're going to do a little bit of demos. We're also going to do a little lab that we're not really going to do a write-up on, but we're going to follow the lab thing so you can actually experience a redox reaction on your own. That's sort of cool. So we're going to do that. All right. There's also one more type of reaction. It's called an acid-base, but we won't get to that one until Chapter 9. So just sort of put that off in your head or put it off to the side. That's one we're going to talk about specifically in Chapter 9. So when we talk about combination reactions or synthesis, they're also known as addition because you're adding things together. So here we have sodium metal, chlorine gas. We're going to get sodium chloride. And there's actually a YouTube video, if you want to go up and look at it, where a guy actually makes salt above his newly popped popcorn with sodium and chlorine gas, and then he eats it. He says, oh, fresh salt, the best way. I don't know that I would feel comfortable eating that, because if there's chlorine gas not reacted, yeah, that's not good to eat. So anyway, but he seems to enjoy it. Oh, there's more stuff on this page. Whoops, sorry. Okay, so combinations basically like boy meets girl, they become a couple. Okay? Now, as we look at the periodic table, we'll consider the metals, the guys, because they like to work in metal stuff, and the non-metals, the girls, so that you can sort of see what's going on when I compare it up here as a cartoon. Okay, next type. So with synthesis, you know what happens after a while, those couples, especially in high school, break up. Okay, so we can get decomposition. And decomposition is just the opposite of synthesis. Now, with synthesis and decomposition, it can go from 2 elements to a compound, or it can go from 2 compounds to a 1 compound. Same thing with decomposition. It can start with 1 compound and go to 2 elements, or 1 compound and go to 2 compounds, or 3 compounds, or 2 compounds and an element. As long as it starts with one thing and breaks down, it's a decomposition. So if it goes from 1 to 2 or more, it's a decomposition. If it starts with 2 or more and goes to 1, it's a synthesis or combination. Okay? So decompositions basically fall apart. This is one where it falls apart into 2 compounds instead of just elements. So we've got calcium carbonate, and we actually did this reaction and it breaks down to calcium oxide and carbon dioxide. So that was the bubbles you saw back in the back when we did our last lab. Okay. Another one that that's just a basic one right there. Another one is copper chloride. If we break it up, it actually goes back to copper and chlorine gas. I think there's one more. So this one right here, CaH2CO3, this is what's in your pop. So when you open up your pop and it starts fizzing, this is what's happening. And so after a while, once you get let it stay out for a while, it becomes what we call flat. And the reason why it becomes flat is because when it breaks up, it's getting more water into your flavoring, and so that's why it doesn't taste quite as good. Oftentimes they use sulfuric acid and ammonium hydroxide. This is one we'd used. A lot of you are saying, well, it says ammonia. Well, ammonium hydroxide quickly breaks down into water and ammonia gas. So when we put those chromatography papers over that ammonium hydroxide, it was actually reacting with the ammonia gas. So that's what was going on there. Okay. Single replacement is also another kind. Single replacement, you have a couple and either a metal or a non-metal, and that part of the couple is replaced. So here we have a non-metal being replaced on the top, and here we have on the bottom a metal being replaced. Okay, so it's a couple and then somebody gets kicked out. Somebody sees somebody better. Okay, all right. Then we also have double displacement. This is like going to the dance and getting mad at your partner and you're going home with somebody else. Okay? Yeah, that's rough. So a boy and a girl, that makes a couple. Now they're switching partners. Okay? We usually leave the positive person in the same place. You'll notice the guy in the wheelchair right here is in the same place, and the guy in the purple shirt's in the same place. The girls did the switch-o. Okay? So that's what we usually do. Yes? Mm-hmm. That's all that was on it? Yep, that's all that was on it. Okay. I just talked about it. Okay, so it can also be an element, or it could be an element and a polyatomic, because a polyatomic can do double displacement too. Just remember, if it's a polyatomic, it usually hangs together as you're moving it. Okay, and we'll go through actual ones later. So another version of it, where with the office up here, I like the really mellow guy here, and then the green guy. But he's like, really not. He's closed. Everything he's doing right here is very closed, and this guy's very open, and this guy's with a very open woman, and he switches. Anyway, all right. So, quick summary. Synthesis, putting together. It doesn't just have to be element and an element. It could be like the Brady Bunch, okay? An element with kids, or an element with something else, and an element with something else, like an element with kids. Brady Bunch, I don't know if you guys, okay? And they come together as a big family. Okay, decomposition can also be like a family breaking apart. It doesn't have to just go down to the man and the wife. It could be a man with some of the children and a wife with some of the children. So it breaks up that way. Single displacement, just replace. It doesn't have to be the girls changing places. It could be two guys changing places. Double displacement, just keep the guys in the right place, switch the girls. Okay? All right. Then we get to one of high school kids' most favorite, and this is combustion. And this is a reaction of fuel with oxygen producing energy in the form of heat or light. So most kids really, really like combustion reactions. We usually, for combustion, I say usually because we can use other things. Yes? Is that what combustion is? Okay. We usually use a hydrocarbon. But we can use other things besides a hydrocarbon. The big thing is it's something plus oxygen yields some oxide plus water. Okay, so if I did it with something with sulfur, I would end up with sulfur dioxide and water. Or if I did it with something, whatever, it's got to have an oxide and water. Most common, though, is the combustion with the hydrocarbons. So this is methane gas with oxygen giving me CO2 and water. And we did that balancing equation earlier, last time when we were doing our reactions. Okay. This is a bigger one. This is butane. So some of you have used butane torches. Butane with lots of oxygen gives me carbon dioxide, water, and a lot of energy. We're going to do several combustion reactions on Tuesday for you guys. and you'll see that there is a lot of energy and light given off. And that's why we can run our cars, because a lot of energy is given off. This drives me nuts. This was just a combustion reaction. I forgot to go in and fix this again. But if I don't have enough oxygen around, I actually get an incomplete combustion where I get carbon monoxide and carbon dioxide and water. This is what the fire department is really worried about in the wintertime when people start up their furnace. Has something plugged the duct coming into the furnace? Is it not getting enough air? If it doesn't get enough air, then it does incomplete combustion, which produces carbon monoxide. And carbon monoxide can be dangerous, very dangerous. So the reason why is because people think that they've got the flu. So here's some symptoms of carbon dioxide. You have headaches, you have nausea. Wait a minute, that's the flu, right? You got dizziness. And then you get breathlessness. You can't quite get a full breath of air, and then you collapse and die if you're not found. Okay, so a lot of people get to this stage because they think that they've just got the flu. So if you think you've got the flu and you go outside and all of a sudden you're feeling better, it's carbon monoxide. If you go outside of whatever building you're in, because you're able to get air. Okay, so what they do with carbon monoxide, because carbon monoxide is sort of what we call a hungry compound, it'll actually attach to where oxygen would in your hemoglobin, and it doesn't let go. And so they have to put you into a pressurized chamber in which they force oxygen into you and force the carbon dioxide off. Okay, so that's with that. Okay, so let's talk about redox reactions just for a little bit. Redox reactions, remember that several of them that we've just talked about are redox reactions. This is when an element changes charge from one side to another. So if I start as an element and it comes into a compound, it's changed charge. Because an element by itself, charge is always 0. So if it becomes part of a compound, usually we have a give and take there, and we have a positive and a negative. So oxidation is loss of electrons, and it becomes more positive. You can see my little video, or my little picture there of a fat guy getting skinnier. So he's lost the electrons, becomes skinnier. And then we have reduction. Gain of electrons becomes more negative. So as you gain electrons, you gain weight. Even though it's small, you gain weight, and you become more negative. So you'll hear me say the bottom ones are just sort of vocabulary. Oxidation numbers are just what we've been calling charges. Those are what oxidation numbers are. Oxidation states are the same as oxidation numbers. It's still the charges. A non-redox reaction is when the charges don't change from one side of the equation to the other side. So that, like in double displacement, they stay the same. Okay, remember that was the only true non-redox reaction. We had two others that we could possibly, like if you had two couples coming together form one family, there's a chance that they don't change charges. If I have one that's breaking down into two compounds as a decomposition, then it's probably not changing charges, and so that could be a redox. But if I go from elements to a compound, then I've changed charge and it's redox. If I go from a compound to two elements, I've changed charges because elements by themselves are 0, and in a compound they have a charge. Okay? All right, we ready to move on? Or we still, nope, we're still doing the head bob. Okay, I'm going to get a drink while you're doing that. Somebody gave me their cold, and I'm not very happy. I want to give it back. I know, I wish I could. Everybody came for the tests on Monday and Tuesday, and they were sick and hacking their heads off, and I got it. And I even Lysoled the room and wiped down with Clorox wipes, dang it. All right, we ready to go? Nope, still head bobbing. So I'm really pushing you to get through notes today so that hopefully we can front load this and be able to get things done. So really homework, the homework part becomes homework. So you really need to do that at home so that when we get to the point where it's, so I shouldn't say homework becomes homework. The Learn Smarts become homework so that when you get to the homework 5A and 5S that you can do them in class and I can help you. Okay? So I really need you to do those homeworks at home. learn smarts at home. Does that make sense? Okay, all right. Looks like we stopped with the head bob. Let's go on. So an easy way to remember this is Leo the lion says grr. So Leo, loss of electrons is oxidation. Grr, gain of electrons is reduction. Also, sometimes they use oil rig. Oxidation is loss, reduction is gain. I actually like the first one just because it just tells me what it is. Both of them sort of tell you what it is, but whatever is easier for you to remember, try and remember one of them, okay? Because they'll help you know what's going. So if I lose electrons, I become positive. Remember that. So I've lost weight, I've become positive. If I gain electrons, I've ate those bonbons, I'm in the corner, I become negative. Okay? Bonbons. Oh, you've never had a bonbon? Chocolate, yummy things. Really good. Not quite as good as the Herzer or whatever. I can't think of what they're called. Anyway, the little gold things. I like those better. But okay, so there's some rules that we have with oxidation numbers. We've used some of them already, but here are the really sort of strict rules. So oxidation state of any element by itself is 0. That includes Braun-Hifkel and phosphorus 4 and sulfur 4. By the way, P.S. by the way, they do it their way, right? Okay, and Braun-Hifkel is just a way to remember that. You could do the upside down L, starting nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen, however you want to remember it. But these always have a 0 for oxidation state. The oxidation state of fluorine is always -1. There is no other charge for fluorine. Groups 1 and 2 on the periodic table are +1 and +2, respectively, with the exception of hydrogen, which can be forced to be a -1 with anybody in what we call type 1 naming. So it could be forced to be a -1 with column 1, column 2, or the slide, because they don't ever take a negative charge, but hydrogen can. Okay? All right, the other rules we need to go over here are oxidation state of oxygen is always -2, except when it's forced to be a peroxide, and that's, again, column 1 basically can force oxygen to be a peroxide, H2O2, Na2O2. So we see that it's forced to be a -1. Gallium, boron, and aluminum are +3. The algebraic sum of a compound always equals 0. So this is always stuff that we've been using, right, when we make our formula. So this should be just review. The algebraic sum of a polyatomic is the charge on that polyatomic. Okay? So if I have phosphate, which is PO4, I know it's a -3. So those have to add to equal that -3. All right. So we're going to practice this because in order to do a redox reaction, you need to be able to really quickly figure out what the charges are. So this is when we use our algebra. Okay? So sodium is in column 1, so it's going to be a +1. I have 3 of them. Phosphorus, did it have a rule? Whoa. Okay, that was fun. Let's go backwards. Come on. I don't know why it went forward, but that's okay. Does phosphorus have a rule? On the ones we just did. Was it in any of the rules we just did? No, it wasn't. So it's going to be an X. We don't know what it is. Plus, did oxygen have a rule? Okay, what was it? Oxygen's always a -2, except when it's forced to be a peroxide, which is not here, because it would have to be H2O2 or Na2O2. It's not that. So it's a negative. Oh my. Okay. So what we're going to do here is we're just going to solve for x, because we know this has to equal 0, because that formula has to equal 0. So we get 3 plus 3 plus x minus 8 equals. Multiplication. So -8. I have no idea what the gremlins are in my computer today, but evidently they're there. And it erases what I do. Okay, anyway. See if I... Okay, so we're just going to talk through this. Okay, so this should be 3 plus x minus 8 equals 0. So if we add minus 8 and 3, that gives us minus 5, right? So then we say x equals 5 because I go to the other side. Is everybody okay with that? So up above here, we could say this is a plus 1. Okay, I guess I'm not writing. A plus 1 for sodium, phosphorus would be a plus 5, and oxygen would be a minus 2. I just need to know the charge on each individual atom. Okay? So let's do sulfur right here. Like I said, I'm going to talk through it because I don't know what is going on with my board. So sulfur, does it have a rule? No. So we put an X. Plus 4 times, what's oxygen? Negative 2. And it's going to equal what? 0. So 4 times negative 2 is negative 8. So I have x minus 8 equals 0. So x is going to equal 8. So sulfur is an 8. Oxygen is a negative 2. So I have to know each individual charge. Would you take a minute and try and figure out the charges for all the rest? And I'm going to reload this and see if I can make it be happy. I'm going to redo the first two so I can see if I can get it there. And nope, it doesn't love me. I don't know what the deal is. Maybe if I shut it all the way down and bring it back up. Let me try that. Oh, not that one. It's not funny. It's sad. Okay, we're just going to have to talk through it. I was going to have you guys come put it on the board, but it's not being happy. Yes?
Okay, so this would be x plus 8.
This whole thing would be equal to 0, just like we did here. And then you just solve for x. So x equals minus 8, or x plus 8. Let's try that again. X minus 8 equals 0, right? And then you take and add 8 to both sides, so x, it would be 8.
And you would take what?
You'd add 8 to both sides, so you could solve for x. And then x would be 8. And x is sulfur's charge, so sulfur would be a plus 8 and oxygen a minus 2. Okay, so on these, you're just trying to find the individual element's charge. That's the big goal of this, that you are trying to find what oxidation charge it is. So what I like to do is I like to just, and I wish I could write on the board because it's just being ornery. I tried to shut it down and put it back up and it still doesn't want to work. So if you can put, like, I know oxygen, so I put a negative 2 above it. I don't know sulfur, so I put an X. Then I come over here, I don't know manganese, but I do know oxygen. Then I go nitrogen. I don't know nitrogen, but I do know hydrogen, but I do know the charge of NH4 as a group. It's plus 1, right? So then I can use that plus 1 to figure out what this is. And I can set this NH4 equal to plus 1 and figure out what the nitrogen's charge is. So if I did that, NH4, and I know it's equal to plus 1, hydrogen's a plus 1, and I have 4 of them. Nitrogen's an X, so X plus 4 equals plus 1. What would X have to be? X plus 4 equals plus 1. It would have to be a negative 3, right? Because if I add negative 3 to 4, I end up with a plus 1, right? So I can put there right there, N is a negative 3. Then I come over here to SeO3, and I know I had 2 positives, so I'm going to have it equal 2 plus. Okay, and then I'm solving for Se, which I don't know. I have 3 oxygens, which are -2 each. So 2 times -3 is -6, right? So I take that, and let me see if I can try one other thing. Because I know it's hard to just listen to me talk. Let's try bringing up a note page and see if I can write with that on. If it's just the, huh?
Yeah, because I'm still not following.
Yeah, I know. It's a lot easier if I can write on the board. The only other thing I can do is, okay, let's do this. See if I can write on that part. So basically what I was saying, let's see if this will let me write now. So we know NH4 as a group is +1, right? So as I'm doing this, I don't know what N is, so I put X. I do know hydrogen is a +1, so I put +1. And I know that this whole group has to equal +1. Okay? So then I just go X plus 4 equals +1. Subtract 4 from each side. So X equals -3. So I know this is a -3, this is a +1. Now, I've got 2 NH4s right here. And SeO3 had to balance it out. So I know that SeO3 was a -2 charge, right? Because I had 2 NH pluses, so they have to add to equal 0. I know that much. So I don't know what Se is, but I do know I have 3 oxygens at a -2, and that has to equal a -2. Right? So following the algebra, x minus 6 equals -2. Add 6 to both sides. X equals +4. So this is a +4, and this is a -2. So I'm just really fast trying to find out what the charges are. Yes? On right here? Because I knew I had 2 ammonias, and each ammonia was a positive. So SeO3 had to balance that out, so it added to 0, right? So if I have +2 plus what number, and I know it equals 0, had to be a -2. So that's where I got it. Yes?
So are we just adding the SeO3 onto our thing?
This is right here. This is this part right here. I split it into 2 because there are 2 polyatomics that went together.
Okay.
So I didn't know 1 in each polyatomic, but I knew the overall charge of each polyatomic. Okay, so if we go to, let's see if I can do this. Come on. Extend the page then. Okay, so on the next one, PbOH2, okay, I know, I don't know this, X, but I do know that I have 2 oxygens, and each oxygen's a -2, so I can put -2 on the top, and I know each hydrogen's a +1. So I've got 2 +1s. I know it has to equal 0. So this represented my oxygen, this represented my hydrogen. So simplifying down, x minus 4 plus 2 equals 0. So x minus 2 equals 0. So x equals a +2 because you'd add 2 to both sides. Okay, I'm shortening it down a little bit. You can do it as fast as you can. You don't have to write down each step because you want to be able to do it quickly. Okay, I'm going to move this over a little bit. Actually, no, because I got another one right behind it. So the sulfur right here that I was doing before and trying to talk you through. Okay, sulfur we don't know. Plus 4 times oxygen is -2. It has to equal the charge that's given. Okay, so then I have x minus 8 equals -2. Add 8 to each side. I know you're trying to do it fast. And x equals +6. So the sulfur is a +6. The oxygen is -2. Those are their charges. Okay, yes. Whitney.
So whenever it has the charge at the end of it, that's what it has to equal?
Right, and if it doesn't have a charge, it's 0. Yes? That was given. Right here. So if it's given, that's what it is equal to. This is oxygen's charge. This right here is where I got that. Does that make sense? Okay, so let's do this other one down here. The chromium Cr2O7, 2 negative. So, taking each thing, we're going to go chromium. I don't know what it is, but I have 2 of them. So this time I'm going to have to do 2x. And that almost worked. Okay. Plus, I'm going to have 7 times oxygen, and I know oxygen's a -2, so I'm going to put a -2 here. Equals, it had an overall charge, so I'm going to put a -2 here. Okay, now trying to simplify, 2x is going to equal -14, or 2x minus 14 is going to equal -2. Add 14 to both sides. We get 2x equals 12. Divide both sides by 2, and x is going to equal 6. So here, chromium is a +6 each. Okay? So it's just algebra. We're just doing math. So if we go to the next one, let's see how we do on this one. I'm going to give you a few minutes to head start me. Fe2O3. What do you know? What don't you know? Try and figure out what you don't know. Okay, don't look up until you're ready. I'm going to put it up, but don't look up until you've got it done. Okay, got it. Thumbs up. Don't got it. Thumbs down. I'm sort of still lost. Ah, yes, thumbs up. I love it. Okay, so the only other ones, did we get all these other? Oh, FeO2. Try that one. And the MnO4 minus. If you haven't done it already, do it real quickly. I'll do the MnO4 minus first, and then I'll do the FeO2. Again, don't look up until you have done it yourself, unless you're lost. How do we do on that one? Thumbs up, I got it. Thumbs down, I didn't. Thumbs sideways, I'm still trying hard. Okay, got a couple sideways on that one. Okay, so now we're going to do FeO2. So give yourself try and get it done. Then we'll look up when you're done. I'm going to give you a few seconds head start. Okay, how do we do on this one? Got it? Thumbs up, don't have it, thumbs down. I'm still trying to figure out what in the heck you're doing, thumbs sideways. Okay, we got thumbs up, that's awesome. Okay, so we're going to go ahead and go forward and see what we can do with next. So this is a little fuzzy, but basically we have to figure out what the charges are. So hydrogen is going to be +1 on both sides. It didn't change. Okay, so that's why it doesn't have its thing there. But I usually go ahead and write +1. I'm going to see. Hopefully it let me. Darn. Okay, it didn't. So you would write +1 on both of those. I like to see all the charges. And I look for things that change from side to side. So carbon went from a -4 to a +4. It changed. Okay, oxygen went from a 0 as an element to a -2, both places it is over here. So it changed. I have to make sure that the number of electrons lost is equal to the number of electrons gained in a redox reaction. So carbon lost 80 electrons. Oxygen, there were 2 of them, And they each lost 2, so that's 4. But you'll notice in front of these, I've got an extra 2 that went through. So that gives me 8. Okay? So let's go forward. Let's look at this one. Okay? Really quickly, figure out the charges on this. You should be able to do it fairly quickly because I gave you an easy one. Write down the ones you know for sure. First, any element by itself is 0. That includes Braun-Hifkel. Hydrogen in a compound is a +1. Oxygen in a compound is a -2. That leaves you only one that you don't know right away. So write the charges right atop and connect the thing. Well, I already connected the things for you that we're changing. Again, I'm going to try and write. We'll see how it works. So the other stuff came in. It's okay. So you'll notice that oxygen was a -2 and it was with copper, so I know that copper had to be +2. That was a real quick, easy fit, find. So as I'm looking, copper went from a +2 to a 0, and hydrogen went from a 0 to a +1. So copper gained 2 electrons, and each copper lost 2 electrons, and hydrogen gained an electron. But there were 2 hydrogens going on that path, so it gained 2 electrons. Does that make sense? Okay, so another redox reaction is like when we're doing zinc and copper sulfate. You can see the copper sulfate in the solution. It's blue. And as the reaction progresses, the copper is going out of solution. You can see it going clearer and clearer because the copper now is plating out on what was the zinc. And it'll come to a point where the copper is so deep on what was left of the zinc that the zinc can't react. Okay? And you can see that zinc is going from a 0 to a +2, and copper is going from a +2 to a 0. Now, which one's being oxidized and which one's being reduced? Good. Zinc is being oxidized because it's becoming more positive. So think OxyClean, positive, okay? And copper is being reduced because it's becoming more negative, okay? All right. So we also have what's called oxidizing agents and reducing agents. This is how I think of it, a bride and a groom, okay? So if the bride is being oxidized and the groom is being reduced, then in order to be a bride and groom, they have to have the other one. So the groom is being the oxidizing agent and the bride is being the reducing agent. Because without each other, they can't do each. So that's how I think of it. So it helps me keep it in my head straight because what's oxidized is the reducing agent. What's reduced is the oxidizing agent. Okay, because they're forcing the other thing. Because they have to come in pairs. Okay, so on top we have the oxidizing agent. Oftentimes we just use OA when we're doing writing equations and we're connected the two. Rather than write oxidizing agent underneath because it's so small area to write, we write OA. Reducing agent is the thing that's being oxidized and it is the RA. So they're opposite. Okay, if I'm an agent, I'm forcing somebody else to do that while I get to do the opposite thing. While you're doing that, I'm just going to put up the charges on this one. We just saw this one, so I'm hoping I can write this up here without too much being really, really careful here. Oh. Not even going to try and erase. Okay, so then connecting side to side, we had the carbon and we had the oxygen, if you remember right. And the oxygen went to 2 places. So the carbon was becoming, that should be a +4 over here. Nope, it's a -4 over here. This is a +4. So the carbon's becoming more positive, so it is oxidized, but it is the reducing agent. Darn. Okay. over here, this is being reduced. So oxygen is my oxidizing agent. This is a fun little thing to do. Okay? So you should be able to look at an equation, and after you figure out the charges, be able to see what's changing and tell me what is it happening to. Is it oxidized or reduced? And if it's oxidized, remember it's the reducing agent. If it's reduced, it's the oxidizing agent. Okay? And just that marriage thing helps me to get it straight in my mind. So if she's being reduced, okay, so if I'm being reduced, I'm forcing somebody else. If I'm the bride, I'm forcing somebody else to be the groom. Because I can't be a bride unless I have a groom, right? So I am the bride, but I'm the groom agent. And the groom can't be a groom unless he has a bride. So the groom is the groom, but it's the bride agent. Okay, does that make sense? Okay. All right, so going forward here. Properties of oxidizing agents. Oxidizing agents will gain electrons, so they're basically opposite of, so oxidizing agents are the ones that are being reduced. And reducing agents are the ones that are being oxidized. So you could also put at the top of these columns, oxidizing agents, this is reduced. And properties of reducing agents, this is also oxidized. Shoot. Yeah, so the reduced is the OA, the oxidized is the RA. So at the top, reduced is what I'm doing, but I'm forcing somebody else to be oxidized. And at the top of the blue, I'm the oxidized, but I'm forcing somebody else to be reduced, so I'm a reducing agent. So those properties also are what happens when we're reduced. So we already talked about them sort of. If I gain electrons, I'm reduced, I'm eating bonds at the quarter, I become more negative. Okay? If I'm oxidized, I've lost electrons, and you remember electrons are negative, so if I lose them, I become more positive, and I become oxidized. Okay? Have you got that? Any more head bobbing?
Yes.
I wish my board would let me. I'm going to have to shut everything down after you guys this period and try to bring it back up again. Okay, so going forward, batteries are redox reactions. We just force the electrons to move through an outer shell, through a wire, so that we can get a current, so that we can run things. Okay? A regular simple battery, or dry cell battery, has magnesium oxide, ammonium chloride, and zinc. Usually have a zinc rod. You have, or a zinc foil, if you've ever opened up a battery, depending on what battery it is. They'll have a zinc foil on the outside layer. They have some moist stuff that lets things transfer back and forth, and a graphite cathode. These are the cheap dollar store batteries. Okay? So they don't last very long. They can't be recharged. They can't do anything like that. These are the button batteries. So in a button battery, you're actually having zinc and mercury. And this is why button batteries are bad to just be tossed, because that mercury can get in our water system. Because if you put it in landfill, it leaches out. And then this is your phone batteries, which have lithium iodine in it. And there was a lot of problems with the Samsung version of that lithium ion battery, that it got too hot and would burn out. Yes? Not necessarily. That's a old wives' tale, or new wives' tale, whatever you want to call it, because it's new age. Sometimes it will, sometimes it won't. It's depending on what's wrong with the battery. Okay? And why it's gone out. So one of the other things that I wonder if I put. Okay. So one of the other things we use for batteries are pacemakers. And pacemakers have done a lot of innovation and change over the years. Basically, it's also a lithium battery, a lithium iodide battery that will last a long time. Usually lithium batteries last longer. They're looking at getting a battery-less device, which they basically add like a circuit breaker to the heart. And I'm not sure all the chemical implications there, but they're working more and more on getting something that will not be rejected. So if you've ever seen a pacemaker rejection, it's a really nasty red rash, and then that goes through the whole body. And if a person needs a pacemaker and they're allergic to the metals in it, that causes a lot of problems. So on the medical side, we're still trying to find batteries that work within the body system. Okay? All right, so we're going to skip that. We're going to go to here, redox reactions in everyday life. So every time you eat food, yes?
What was the definition of pacemaker?
So pacemaker is just a battery that's put into your body that supplies electrical current, because your heart works on electrical current when your heart has an arrhythmia, when it has not a solid rhythm. So it sort of shocks the heart. Okay? Redox reactions in everyday life. Every time we eat, we're doing a redox reaction. Our body uses that energy from that food. It oxidizes it. It causes byproducts. Every time we breathe out carbon dioxide and a little water. And we have the energy left in our body to keep moving and keep talking and doing things. We also have redox reactions that power our home with electricity, our cars with our batteries, and our bodies. So there's redox reactions all the way around us. They're everywhere we go. Okay, so we need to be able to balance the following and then determine the oxidation numbers and then follow the equations and then identify what is being oxidized, reduced, the reducing agent, and oxidizing agent. So I'm going to try and bring up that other little paper for me so I can write underneath. And go ahead and try on your own. Get up what you can. Do what you can. And I'll do it down here on this one below it, because it looks like I can write on this page, but I can't write on the one below it. Okay, so balance it first. You should be able to balance, right? Okay, how'd you do? Just with the balancing, that's just practice. Okay, then we go really quickly and we do the charges. Should be very easy. With the elements by themselves, they're 0. So 0, 0. Oxygen's a -2. And aluminum would have to be a what? So -2 times 3 is 6, plus 2 times what is 0? So it'd have to be a +3, right? Because they each need to make 6. Yes? How did I get the 6? Okay, so if I go back, aluminum and oxygen, it was 1 and 2, and then I put a 2 there. And then I went to oxygen and said, oh, there's a 2 and a 3, right, originally? Not looking at my reds. There's a 2 and a 3, so common factor is 6. So I times this one by 3 to get to 6, which I did, times this one by 2 to get to 6, but when I did that, that changed it to 4. So then I had to go back and fix the aluminum. It should have been 4, not 6. Thank you. 4. Okay, thank you for checking on me. Okay. So then we went back and we do the charges. And I connect side to side what's changing. So aluminum changed to be more positive. What was that? Oxidized or reduced? Oxidized. Okay, it became more positive. So this is my RA, my reducing agent. The other one, oxygen, went from a 0 to a -2. So it was reduced, and it is my oxidizing agent. So you should be able to do that on any equation. So go to the next one. I'm going to let that be up there for a minute, and then I'll come and help you with the next one. but try and do it on your own first. Balance it. Did you have a question?
Oh, I was stretching.
Stretching? Okay. Nope, you're good.
So we're doing number 2 now?
Yeah, do number 2. So balance it first, then find out all the charges, and then once you find all the charges, then decide what's oxidized and what's reduced. I'm just going to rewrite the equation right here for a minute. Yes? I'll just come help you first.
Do I multiply them? Right?
No, you add them. So it'll be 2 plus 4 is
Oh,
6.
I don't multiply them. I add them when there's
If,
when they're on
if
the
they're,
same side.
and they're different compounds, yes.
Oh.
Okay, I'm going to do it slowly up here, so if you get stuck, you can do it with me. So balancing that should have been easy, right? Okay, now do the charges. If you haven't done the charges, do the charges. Okay, go with what you know for sure. So any element by itself is 0. Oxygen is always a -2 unless it's by itself. Hydrogen is always a +1. So the only thing I had to figure out was carbon, right? And that was fairly easy because oxygen, the first one's a -2, so carbon had to be a +2. On the last one, hydrogen's a +1. I have 4 of them, so I have to have a -4 to balance that out. Now the next step is to connect what's changing from side to side. So we know the carbon's changing. What's happening to the carbon? Oxidized or reduced? Reduced. Good. It is reduced. So this is the OA, oxidizing agent. Okay, and I'm going to use a green here. Hydrogen is going from a 0 to a +1. So what's happening to it? Oxidized. And it is the RA, or reducing agent. Okay, go ahead and do the third one. Go ahead and do the third one. The charge just tells me if it's oxidized or reduced. So if this, it doesn't add up to 0, adds up to a -2, adds up to a -1. And I'm not pulling the states up here. I'm just going to write the chemical formulas so we have less stuff. So that one shouldn't have been too hard to balance, right? Okay, go ahead and put the charges up. If you haven't put the charges up. Yeah, I'll pass on this side. Okay, so you did have to do a little bit of algebra on that one. It wasn't quite as easy to find the charges. So, but you only had to do 2 sets of algebra equations. So if they get a little hairy like that, write it down. Do the algebra for it. Okay, I didn't just all of a sudden in my head try and figure it out. Probably could have with the SO4, but I wanted to just see how I was doing it. Okay? So when you're doing charges, you don't worry about coefficients. Okay, so I'm ignoring the coefficients. I do care about if it has a charge, though. So you see how it was, I gave it a charge. Is everybody okay? Do you understand how I found the charges? Okay. All right, so the next thing is identifying what's changing. What's my oxidized, what's my reduced? Okay. So I know sulfur's changing from one side to the other side, and I know iodine's changing from one side to the other side. Okay? So what charge do I have? Hey guys, come on. So what's happening with sulfur? What's going on with sulfur? It is. It's becoming more negative, so it is reduced. So it's also what? Oxidizing agent. Good. Iodine, what's happening to it? Becoming more positive, so it's oxidized, so it is the reducing agent. Okay? Are we getting this? Awesome. Okay, so going forward, next page. There's some more practice. I want you to see what you can do. We're only going to do a few minutes, so let's just do the first side and see what you can do with that real fast. That'll leave the second, so the first column. So the second column will be yours if you want more practice. But go ahead with the first column. I tried to make it fairly easy so we could do it quickly. And I'll bring up my thing again and put it on the left so I can rewrite the equations since it's being ornery. So get a good head start on me. You're doing everything we did before. You don't even have to balance these equations. They're already balanced for you. Okay, so charges are the first thing you want to do. Remember, any element by itself is 0. Then look for anything that you know. Like bromine will be a -1, so, and then cesium is always a +1. Oxygen is a -2, so I have a -6. So I need to make iron be a +6, so I put a 3 there because there's 2 of them. Fluorine's always a -1, so silicon has to be a +4. Hydrogen's always a +1, so chlorine here is a -1. Magnesium always a +2, so each chlorine's a -1. So I've written down everything I know for sure. Now connect the things that are changing side to side and label them. And I'm all about the color, so if you want to use the color pencils, you can use the color pencils. Or if you just want to label, you can just label. Okay, so looking at these really quickly, cesium went plus, so that was oxidized, and it's the reducing agent, right? So all of my blues, I sort of color coordinated, are my oxidizing agents, and oxidized and being my reducing agents. So oxidized, my reducing agent. Oxidized, my reducing agent. That leaves the reds to be what? Reduced and my oxidizing agent, right? So oxidizing agent and it is reduced. Oxidizing agent and it is reduced. Oxidizing agent and it is reduced. Okay, so you should be able to do that with any equation that I give you. Most often, in fact all the time, when you have an element by itself on one side and it's not on itself by itself on the other side, you have a redox. Yes, what's your question? Okay, are you getting what we're doing? Do you know how to label? How to find the charges? Label the oxidized and reduced? Okay. Uh-huh. Right. The only way I could do the +4 charge is because fluorine always has a -1 charge, and there's 4 of them. So I know silicon's taking its +4 charge. That's how I did it. It wasn't because it's in the 4th column over, and I know that we've used that plus or minus 4 there. It's not that reason. It's because of what it was with. Okay, were you okay to move on? Everybody understand how to do this? Okay. If you need to, again, I will have this up on the web so that you can go back to Canvas and look at it again. It will be through YouTube because that's the easiest right now. For some reason, the OneDrive, have you guys been having trouble with the OneDrive? General was telling me they're having trouble with the OneDrive. So I put it up on YouTube. You just can't use the service here at the school to see the YouTube, which is sort of sucky. Okay, sorry. Okay. So we should be able to just look at a reaction and be able to tell if it's redox or non-redox and what type it is. So, look at it. Compound or element? Compound or element? Compound or element? Compound or element? So you have a compound and a compound making a new compound and a new compound. What type of reaction? Double displacement. DD. So, is that a redox or a non-redox? Non-redox, because I don't have any elements by themselves. They didn't change charges.
So wait, it's redox if it's like a compound?
It's redox if I have an element by itself and it goes into a compound, or a compound and it goes into an element.
And then non-redox
When the charges don't change side to side. Okay, so what's the next one, guys? What do you think? Compound, compound, yields, compound, compound. Double displacement. And it is non-redox. That's the only one that's non-redox for sure, that I don't have to double check. Okay? All right, so this one, we've got a carbon, or hydrocarbon, plus oxygen, yields CO2 and water. What type of reaction was that? Combustion, yes. It's a combustion reaction. Is it a redox or non-redox? Redox, you're right. Okay, here we have an element, or single person, a couple, a compound, using a new couple and a new element by itself. What type? Good, single displacement. Okay, sometimes they call them replacement, so don't get thrown off by that. So if it's single replacement or displacement, same. Double displacement or double replacement, the same. Redox or non-redox? Okay, good. Compound yielding a compound and a compound. Compound yielding a compound and a compound. Good. Decomposition. Falling apart. Okay. Now, this is where we got to be careful. Did the charges change side to side? So calcium is a +2 always. Whoa. I tried to write on there. Calcium is a +2 always. Oxygen's a -2 always, right? So I have 6 negatives with a +2. That gives -4. So carbon had to be a +4. Okay, let's look at the other side. Calcium's always a +2. Oxygen's a -2. Oxygen's a -2 with CO2. That's 2 -2s. That means carbon has to be +4. Did it change charges? No, they were the same. So this is a non-redox. Decomposition can be either. The hint here is if it goes down to an element or starts at an element, goes to a compound, that's going to be redox. Okay, next type. Element, element, compound. Which kind? Synthesis. You're putting it together. Redox or non-redox? Redox, yes. Okay, next one. Compound, compound. Yes, compound, compound. Double displacement. And redox or non-redox? Good. Next one. Compound element yields compound element. Single displacement. Good. Okay, and redox or non-redox? Good. So pretty easy once you get it in your head what it is, right? Okay, let's go forward. There's some more that you can practice with. I'm not going to do those with you. We're just going to go forward. We need to be able to write an equation. So now we're taking it even one more step. They're giving us the equation in words, and we need to use what we learned the last 2 chapters to put them into chemical compounds, then to balance it, then to be able to tell what type it is, then be able to tell if it's redox or non-redox. So, silver. I like to use a little bit of space above or below, it doesn't matter. So silver is a plus. This is going to be fun. Okay, let me bring the other thing up because it's going to be ornery. What? One more. Okay, we'll put this right here. Sorry for the extra time. I was working so well for a minute, and then it just decided to do it again. Okay, so silver is Ag, right? What does the 1 tell me? The charge. So I like to do this anyway because it didn't really give me enough room on here. So I like to do like that scratch piece of paper we use for balancing. I do that for this too. So it's a +1. Nitrate. What is nitrate? NO3. What charge does it have? -1, right? So I can just smash those two together. So I got AgNO3 plus hydrogen sulfide. What's hydrogen? H plus. What's sulfide? Just S. IDE says it's the element, with exception of cyanide and hydroxide, right? So sulfur has what charge? It's 2 away from being a noble gas, right? So I'm going to need 2 hydrogens to go with a sulfur. Now, hydrogen sulfide is the way that we call it pharmacy, or not pharmacy, supermarketese. That's really not the right name for it. What's the right name for it? Well, we haven't learned that because it's acids, so we'll just keep going. We'll get to that in chapter 9. Okay, gives. Silver 1, so I've got Ag again, plus, and sulfide again, 2 minus. So I'm going to have Ag2S plus nitric acid. I'm going to give you that one because we have not talked about that. That's HNO3. Okay, now I go through and balance it. So I say, okay, I've got Ag, I've got N, I've got S, and I've got H and O. So side to side, 1 silver, 2 silvers. So I'm going to put 2 in front, makes 2. 2 nitrogens now on this side, 1 nitrogen on that side, so I'm going to put 2 in front over here to make 2. Sulfur's next, 1 on each side. We're good with that. Then hydrogen comes next, so I've got 2 on this side, 2 on this side. Oxygen's next, 6, and 6, and we're done. Everybody okay with that? Okay, so I'm now going to erase all this stuff on the top because I'm going to use the top to put my charges up so I can do figure out what's changing, if anything, side to side. So, First of all, I look and say, wait a minute, do I need to do that? Compound, compound, yields compound, compound. Do I need to know the charges? No, why? What type is it? Okay, so reaction type, double displacement. Redox or not redox? Non-redox. Okay, so let's go to the next one. You go ahead and do it before me. See if you can do that by yourself. Let me see if there's one that I need to tell you about. Nope, you're good. See if you can do that one by yourself. Okay, we're trying to do this on our own. See if you can do it. Remember, the Roman numeral tells me the charge on copper, not how many coppers I have. 10 is right here, number 50. You got to look at what it's with to see what the charge is, because it's in the lower P. Still can be seen, so we're good. Okay, how do we do on this one? Were you able to write the formula for the equations? Okay, once you looked up sulfate, I really didn't need to show sulfate again because that 10, by the way, is a +2, not a -2. Just didn't want to, there, that's a plus. So once I got the sulfate, I know it was with copper and I know it's with tin, and both of them are 2, so I know it's going to work out. So, what type of reaction is this? Single displacement. Do I need to do the charges in order to tell me if it's redox or not? Do I? Anytime I have an element by itself, it's going to be a redox reaction because that element is 0 by itself, and when it's in a compound, it has a charge, right? So here, I don't need to do the charges to figure out if it's redox or non-redox. Now, in order to be able to find out if what is being oxidized and what's being reduced and what's the oxidizing agent, what's the reducing agent, yes, I would need to. But I know these are zeros, and I know that was a +2, and I know that was a +2, right? Because they gave it to me. Sulfate stayed the same. So those are the only things that are changing. What's oxidized? The tin, right? Tin is oxidized because it's becoming more positive. And it is the Ra. What's being reduced? Well, the other one, copper. Because it's going from a +2 to a 0. So this one is being reduced, and it is my OA, or my oxidizing agent. So you could tie all of that in, okay? I am leaving you some more so you can practice so that you can go back and see if you're doing it right or not. Let's go on to the next section, because I wanted to make sure you had some that you could practice on your own. This section now, we're adding one more step, okay? And this is the last one I'm going to do today. But we're adding one more step. We've got to predict what the products are, okay? So, let me bring up my little paper again because it's being real dumb. Of course, I can't bring it up from over there. Okay. Get me a clean sheet and bring it down below it. Okay. Looking at this, what type of reaction do you think it's going to be? Just looking at it. Single displacement. Good. So I'm going to say it's a single displacement, but I've got to finish the equation. So I need to figure out, do I have 2 guys and a girl, or do I have 2 girls and a guy? So I do need to know the charges. Well, copper by itself is 0, right? And over here, silver, oh, it's an Ag2, thank you, sorry. Silver is a +1 because SO4 is a -2. And there's 2 silver, so it has to balance out. So then I look and say, okay, where's copper on the periodic table? It's a metal. Is it going to be a positive or negative charge? Positive when it combines with something. So it's going to switch with silver. Okay? So now, if we go a little bit farther, there's an activity series of metal, and this really wouldn't happen. It would go the other way, but we're going to force it. Okay? We're going to pretend like we put some electricity or something and forced it this way. All right, so we're going to move copper in where sulfur was, or sulfate was. I know the charges except for copper. Copper basically will take a +1. If it's forced, it likes +2. So that's one of the things I sort of need to know, but I'm just going to put it up here. So say it's a +2 that it will go to. So on the other side, I'm going to put copper and sulfate together. +2, -2, don't have to do anything but smash them together. So CuSO4. And silver got kicked out by itself, and it's not a Braunhilfel, so I just write Ag. Then you got to remember to erase these charges on the top because they cannot be part of the balanced equation. As I look at this, there's only a couple things I need to do, or one thing I need to do. What needs to be fixed? Yes?
Are you not moving the 2?
No.
Or H
Because that 2 balanced the charge on sulfate. Okay? So now I'm going to balance the equation. So I just need a 2 on the Ag, right? And then I'm balanced. Okay, so now, without writing the connecting dots, what was being oxidized? What became more positive? Copper. Copper went from 0 to +2. So I can say right now, without doing anything else, I know copper was oxidized. That makes it the reducing agent. What was being reduced? Ag, because Ag went from a +1 to a 0, right? So if it's an element, all I have to do is say, oh, is it an element that's going to become part of a compound? And if that element is in the front, it's becoming positive, then I know right away, oh, if it's becoming positive, it's oxidized, and it's the reducing agent. I don't have to go through each one and figure it out. Okay, does that make sense? So we're doing a little bit of shortcut. Okay, let's do the next one right here. How many of you have reached the point in math where you know what FOIL is?
Yeah,
Okay, what does FOIL mean?
it's just where you like basically distribute everything.
Okay, first, inside, outside, last, right? Or first, outside, inside, last. Either way. We, in chemistry, use OI. Outsides and insides. Okay, that tells us how to put it together. So we have NaI plus CaCl2 going to. Okay, really quick, charges. Sodium, +1. Iodine, -1. Calcium's in a +2 column. That means chlorine has to be -1. When I say OI, what I'm saying is sodium is now going to go with chlorine, and calcium is now going to go with iodine. The first ones stay the first ones. So basically, they just switch the negative partners. So over here, I'm going to write sodium is going with chlorine, +1, -1, don't have to do anything. Plus, calcium is now going with iodine. Calcium is a +2, iodine's a -1, so I do need 2 iodines. So I'm balancing the charge of each compound. Yes? Why are we what? I'm balancing the charge of each of these. So this is a +1, this is a -1, this is a +2, this is a minus. So I have to balance the charge. Okay? All right, so then I would go through and balance it. This is a double displacement, right? So what do we know about double displacement? Redox or non-redox? Non-redox. So all you'd have to do is balance here by putting a 2 and a 2. And then you could go on. Okay? All right, we will do some demos and finish up hopefully next time. Okay? Do your Learn Smarts, the first 4, by next time.
Main office. Tyler Hernandez, Aiden Hernandez, Desiree Trammell, please come to the main office. There's a minivan.